Okay, we'll go ahead and get started. So we're starting module 2 today. So this focuses on oxidation state 1 functional groups. So alcohols, amines, ethers. So commingled with this are our oxidation state 2 and 3. And so what we're looking at really now is oxidation reduction reactions. And so the module is organized in that concept of either reducing or oxidizing. So really, if you understand just how to count that, what you have to learn is the reagents that will do those things. And so you need to pay attention to like the molecular formulas. So what we'll do today is look at reducing agents. Those have an excess of hydrogen. So hydrogen in the form of hydride. So we'll talk about reactivity principles based on what you see in the reagents. We're going to sort of review the fundamentals of alcohols today. Any questions before we get started? So we at this point should know that alcohols contain the hydroxyl group. So that's the OH. And, we can abbreviate that ROH, where R is basically the rest of the molecule. So we'll talk about the nomenclature. How do we know that OH is in a molecule using IR, NMR, that sort of thing. And then we'll get into how do we access alcohols? What are some of the reactions? So alcohols are named according to finding the longest alkane chain length, and then you drop the E and add OL from the alkane name. And as the chain gets longer, you have to specify where on the chain the alcohol is. So as we see in the first column here, once we get above 2 carbons and above, then we can have different constitutional isomers of that molecular formula. And so we have to specify where along the chain the OH group is, and then we can classify is it primary, secondary, or tertiary. So you can see from the name, methane becomes methanol. So again, pay attention to what the suffix is telling you of the IUPAC name. So in the nomenclature rules, the parent is the highest oxidized carbon. So in methanol, it's an OH group, so that carbon is at oxidation state 1. When we learn about polyfunctional molecules, so for example, we'll talk about carbohydrates at some point. So those are carbon chains with a lot of different alcohols, and then on that chain is a higher oxidized carbon. So it can be at an aldehyde or acid oxidation state. So the higher oxidation state gets the parent or the suffix of the chain. So keep in mind all of those things that just the name is telling you. So we see the structure there is CH3OH, molecular weight, and then melting and boiling point. So the influence of the hydroxyl group on a molecule is that because it can hydrogen bond, it definitely increases the boiling point quite a bit. So we'll learn about ethers as well. And so when you remove that hydrogen bond capability, the boiling points typically decrease. So ethanol is the 2-carbon alcohol. And then when we get up to the 3 chain, now you see there's 2 constitutional isomers. And so for 3 carbons, you can have the OH group at the 1 position, or it can be at the 2 position. And so that's what that number is in the name, where you're specifying the location of the OH group. In terms of the oxidation state, the number in blue there, because the carbon is sigma bonded to oxygen, they're both at oxidation state 1. The class of alcohol, that's when you're looking at, so by class, you're looking at the carbon bonding to the OH group and then determining how many other carbons is it bonded to. So this one would be a primary, and this one would be secondary. So if the carbon had 3 other carbon groups, it'd be tertiary. So one thing I want to point out for the 4-carbon chain, notice now you have the possibility of primary, secondary, tertiary. Look at the boiling point trend. So the boiling points are decreasing as the substitution pattern is increasing. And the way that I like to think about it is, so primary is like spaghetti, and tertiary is like M&Ms. So the primary alcohols tend to have higher boiling points because they have these long chains that can wrap around one another. And when you're boiling something, you're adding heat to break those non-covalent interactions. And if they're really wrapped around one another, it's harder to break them. When they're secondary, they're more spherical. So if you think of like a bowl of M&Ms, just sort of the surface of that sphere is touching. And so that's an easier interaction to break. So the boiling points tend to be lower. So when we get to module 5, these non-covalent interactions will be really important for us when we start talking about biomolecules and how large proteins and enzymes function. They function primarily through non-covalent interactions. And understanding the organic chemistry part of that will lead you into biochemistry or cell and molecular biology if you're taking those classes. So let's do a little practice in naming here. So given the structure, what's the name of the alcohol? The first thing we want to do is find the longest carbon chain that's bearing the OH group. So I've highlighted that in red. And if we count that, we get 6 carbons, so it's going to be a hexane derivative. So immediately we can eliminate C and D. Now the difference between A and B is the numbering of the substituents along the chain. The highest oxidized carbon on that chain is the one bearing the OH group, so that's going to be the parent, and it has to get the lowest number. So we would start numbering from left to right. And so this would basically become 3 hexanol. So the 3 tells you where the OH is located. So now that we've taken care of that, we have one more thing left. So that group right there, it's 1 carbon So methane will become methyl. It's on carbon 4, so we just shove that in front of the 3-hexanol. So that would eliminate B. So either of these, so choice A writes it different than I wrote it. This is probably more correct nowadays, where you're putting the 3 right in front of that main functional group, but you can stick it in front of the hexanes. It's the same thing. So as we go up in oxidation state and we learn, 2 and 3 and that sort of thing, we'll review the nomenclature as well and how do we decide what gets the main parent name. So this question was about that trend where you're looking at the different class of alcohol and explaining why the boiling point would end up decreasing. So if we draw these out, that would be those 3 there. So you can see that we have primary, secondary, and tertiary. And I think the best fit for this is choice B. When the hydroxyl group is at the 1 position, the boiling point is typically higher. So when you're thinking about these and maybe you see it on some exam in this class or another class, molecular weight really is not a significant contributor to any changes in physical properties. So again, what does impact? It's the functional groups, and then what non-covalent interactions are present. So functional groups, and their non-covalent interactions. So the most common one that you know now is hydrogen bonding. So donating, accepting. When we get into module 5, we'll learn about other more subtle ones. But the sum of all those subtle non-covalent interactions leads to the changes in physical properties. So we know that alcohols have the hydroxyl group. But how experimentally do we know they're there? Yeah.
What was that last word you wrote on top in the last slide?
Extent.
Okay.
Sorry, it's a bit sloppy. This nib in that screen, it's too slippery. It doesn't have enough friction to mimic paper. So how do we know the OH group is there using the data that we've learned? So IR really is the best technique to show us the presence of the OH group. So it has that nice broad stretch in region 1, and that the broadness is due to hydrogen bonding. And again, on a subsequent slide, I'll show you how that interaction is depicted chemically. So when we're talking about a broad stretch, why does it span so many wave numbers? What does that do to? Mass spectrometry. If you take Chemistry 404, which is structural elucidation, you'll learn more about what this means, possible loss of water. It's highlighted in yellow. So in terms of the stoplight system, green is pretty confident, yellow a little bit, and red, it's not very useful. It's basically a fragmentation of the parent that's going to lose 18 mass units. So you'd have a fragment M minus 18 that would indirectly tell you that alcohol is there. Proton NMR again is in yellow. You might see a singlet that corresponds to that H of the hydroxyl group that would integrate to 1. But the issue with NMR is that protons bonded to heteroatoms tend to exchange. So what I mean by that is you run these samples in a deuterated solvent so that H becomes a D, a deuterium, and then you would not see it. So NMR is dependent upon pH, solvent, concentration. So you could see it or you could not. So that's why it's yellow. Carbon-13, if you have the carbon signal between 30 to 60 ppm, that's usually a strong indicator the carbon's bonded to a heteroatom. And then in that region is typically oxygen. And again, the chemical shift in NMR is due to the, partially due to the electronegativity of what atom is bonded to the carbon. So oxygen, nitrogen, and halogens shift the carbon in different regions. So the OH, the molecule shown here is the 1-butanol. So this right here is the telltale sign of the OH group. So that's the OH stretch. So there's the stretch itself. The reason it's broad is because this blue interaction, that's the non-covalent interaction, the hydrogen bonding. So you have the OH sigma bond itself stretching. Then you have this hydrogen bond that's sort of pulling the hydrogen in another direction. And what would normally be a nice sharp peak, it's then broadening it. And what I mean by that is if we go from sort of the baseline and you measure that distance, you see that signal spans quite a large wave number region. And so that's what we mean by broad. And that's due to the hydrogen bonding. So you see that, you can immediately say, okay, it's got an OH group. So the bonding pattern for oxygen is 2 sigma bonds, 2 lone pairs. So from that, we can assign the dipole where oxygen is delta minus and hydrogen's delta plus. that will have implications on acidity. So remember that an OH bond is a lot more acidic than a CH bond. That's due to that difference in electronegativity. And then if we were to draw the dipole itself, that's what that would look like. And that's what the IR technique is perturbing through the light. So the light senses that dipole, it moves the bond back and forth, stretching it, and then we see the instrument signal. So I'll just use water as an example for the non-covalent interaction again. So we typically draw that with like a dashed line. And this would be the donor. So it's donating that OH. And then this molecule down here would be the acceptor. So that lone pair on oxygen is accepting that OH bond. That hydrogen bond's worth about 20 kilojoules per mole of energy. So your normal CH bond is a couple hundred kilojoules per mole. So this is a weaker interaction. But like in water, this is definitely more than 18 grams. So there's a couple moles of water in here. You have a lot of those weak interactions. So when they sum up, it's quite a bit of energy. And so when you're boiling your water at home for pasta, it takes quite a while to get that sort of rolling boil because you have to break all those non-covalent interactions. So as we go through these oxidation states for the functional groups, just keep in mind, the presence of an OH or NH bond, and then when you get rid of that, how is it affecting the physical properties? So the alcohol group itself has two modes of reactivity. And the mode is dependent upon the reaction conditions. So the first one we'll look at is the basicity. So that means the oxygen is going to act as a base. So therefore, it has to react with an acid. And that acid we're going to use is hydronium ion, so H3O+. So we have the two lone pairs. What's going to happen is the oxygen will abstract one. And we're going to shuffle that proton around, so a proton transfer. And so the alcohol that's protonated is now called oxonium. So hydronium, everything's hydrogen, and oxonium, you have a carbon substituent. Notice the formal charge migrates as well. So this is a reactive intermediate. And what will happen is this bond can ionize. So that forms water. And then the plus charge has to be conserved. So it hops over to the carbon. And now this is a carbocation. In the old nomenclature, it used to be called carbonium ion. So things that end in IUM are typically positively charged. the takeaway from this is the medium is, the reaction medium is acidic. So the oxygen has to be neutral or positive. We can't invoke a negatively charged oxygen in acidic medium. So as I said, we're going to start learning a lot of reactions, a lot of named reactions. And yes, it's possible that you can just memorize them. But if you want to relieve the mental burden of having to memorize a lot of stuff, if you understand these reactivity patterns, you're able to better predict the mechanisms by which the starting materials are converted to the products. So under acidic medium, the oxygen will act as a base. So under basic medium, the OH group, the H is now acting as an acid. So it's got to give up a proton, and the most acidic proton is the one bonded to the oxygen. So I'll expand this out. So the pKa is, about 16. We're going to treat that with a strong base. So sodium plus, and then hydride is H minus. So that base is going to abstract this proton. And then the electrons will go on to oxygen. Because oxygen's now negatively charged, it's called an alkoxide. So OH minus is hydroxide. If you substitute that H for carbon, it's an alkoxide. And now under these conditions, that O minus is a nucleophile. So the oxygen has an excess of electrons. It wants to bond to something electrophilic. And so that's typically the SN2 reactions that we learned in Organic 1. So as opposed to the prior slide, now since we're under basic media, the oxygen has to be neutral or negative. So again, here it can't be positive. So as we'll see in some of the reactions we learned today, that's going to be important for the mechanism. And then I'm assuming you've done a couple reactions in the lab already. When you get to the end of the reaction, you typically do a workup. In the workup stage, that's when you're adjusting the pH. So if you end up with an alkoxide, you need to adjust the pH so it's acidic, so that gets protonated, you can form your alcohol. The question in green there, how does base strength affect equilibrium? Remember, the equilibrium always lies to the weaker acid-base pair. So when you're choosing a base, is the difference between the pKa's great enough that you can shift it to one side? So to tie all this together, you're forming these intermediates, oxonium or alkoxide. We examined the reaction coordinate diagrams that plot energy versus time. where along the reaction coordinate does an intermediate lie? Any guesses? What?
At the peak?
No. What's it called at the peak? Transition state. So it can't be A, can't be B, because that's your starting materials. So it's got to be C. It's a well or a valley. So this right here would be an intermediate. So again, it's higher in energy than your starting materials, but it's not the product yet. So it's an intermediate along that pathway. So the higher energy going up to the transition state, that was called the energy of activation. And that's typically the rate determining step. And then you can fall into this intermediate well. So the way to visualize that, is like a little ball. When the ball gets to the top of that hill, it can either go back to the starting materials or it can go forward into the intermediate well. When it's in the well, it can sort of move back and forth in that well. But when it's at a peak, the time it can exist there is so short that once it gets to the top, it's either going to fall forward or backwards immediately. So intermediate just means it's longer lived than a transition state. Any questions? So if we focus on the acidity, so that pK value of the OH group, the range is typically between 15 and 18, depending on what the rest of the molecule is. So the carbon bearing the OH group, what functional group is that part of? Does it make the OH group more acidic? Or does it push it a little bit past 16 to less acidic? Let's look at two examples of this. So cyclohexanol is a secondary alcohol. Phenol is an aromatic alcohol. And the difference between them is a pK of 16 versus 10. So the question you have to answer is, they both have OH, but the phenol is 10 to the 6 times more acidic than cyclohexanol. So why is that? What? So they're both starting with OH. So you really have to compare what is the nature of the conjugate base of each of them. So let's draw those structures out. So imagine I'm deprotonating the H and I'm left with the alkoxide. Now, is there something of those structures that we can use to explain that big difference in acidity? So the pi bonds, what word would we use? Resonance. So remember from module 1 when we were talking about electrophilic aromatic substitution and how resonance sort of dictates where a reaction will take place. The negative charge in the phenol can be pushed into the ring, and so that stabilizes it. So a resonance form can move that negative charge into those different resonance hybrids. And so you're sort of like spreading out the misery. In the cyclohexanol, that negative charge it's stuck on that oxygen. It can't go anywhere. So really we're looking at comparing the differences in the product structures here to explain the original OH acidity difference. So just write a note here, phenol is more acidic. I think that leads to the next question here where we'll draw some arrows. So we'll put some electrons in, we'll put an arrow in, and then we'll explain again the difference in pKa, why it's shifted towards the products. So the alkoxide will have its 3 lone pairs. The alcohol has its 2. And this arrow is telling you that it's product favored. The reason for that, again, this is the weaker acid. And the equilibrium will always favor the weaker acid-base pair. So one of these lone pairs will act as the base to abstract that hydrogen. That's the proton transfer. And then you end up with the phenoxide and the cyclohexanol. Questions? So proton transfers, again, I can't emphasize it enough. It's going to be important not only for this class, when we get to module 5 as well, we'll review it quite a bit then, but also like if you go into biochemistry, the way that enzymes work is they're really shuffling protons around to help activate functional groups and to do carbon-carbon, carbon-nitrogen, carbon-oxygen bond formation. So, when reactions happen in your body, they're not happening with hydroxide, they're not happening with HCl. So you have different protonation states of amino acids that help move protons around. Any questions? So we'll start looking at some reactions and mechanisms now, some best practices for helping figure out the mechanism of a reaction. So if your starting material is your products, and then the mechanism is the pathway by which that occurs. And really what we're interested in doing is understanding the flow of electrons. How do we account for them? So those principles of electronegativity come into practice here. And also recognizing, in these reagents, is there an excess of hydrogen? Is there an excess of oxygen? That gives you a clue about what's happening. So all reactions have a nucleophile and an electrophile. That's the most general sense. If we're dealing with proton transfer, then we just call it acid-base reactions. The nucleophile is an electron source, so that's a lone pair of electrons or a pi bond. An electrophile is an electron sink, something that can accept those electrons. So arrows start from a nucleophile and they point towards the electrophile. That's the flow. We'll want to number the carbon skeleton in a meaningful way so we can keep track of, is this the right number of carbons? Is the ring size correct? Where on the carbon chain are the functional groups? How is the oxidation state changing? A big one is right here. In general, when a new bond is formed, an existing bond must be broken. So these are getting back to your Lewis dot rules. You don't want to be showing, carbon with 5 bonds to it because you're not obeying the Lewis dot rules. As we said, acidic media will always have neutral and positively charged species, and basic media will have neutral or negatively charged species. So there's some subtlety in that we'll see come into play probably on Wednesday. So reactions to review from Organic 1. We have a common starting material here, propene. So we learned about taking that alkene and making alcohols. So the first one here, this would be, say, H3O+. This is hydration. So notice that gives you a secondary alcohol. You can make the primary alcohol through hydroboration, oxidation, and that used BH3, THF, and sodium hydroperoxide. The last one, you get both, a primary and a secondary. This was called dihydroxylation. And that used osmium tetroxide or potassium permanganate. This would be an example of these two reagents here. See how they both have 4 oxygens? So when I look at that, I say, okay, that is an oxidizing agent. Reducing agents are typically going to have an excess of hydrogen or some negatively charged species that's going to do a reduction. We also learned how to take alkenes to make epoxides with MCPBA. And that was that peroxide. So in terms of the mechanism, this oxygen right here is electrophilic, so it's going to accept electrons. The pi bond is nucleophilic, so it's going to donate electrons to that oxygen. And then you end up with an epoxide. So the epoxide is the three-membered ring ether. Yeah.
On the propane 1,2-diol, does that say O5 or 4?
OSO4, KMNO4. And then the last reaction was halohydrin formation. And this was taking bromine and water. So you might have done that in organic 1. You had some alkene, you added bromine water to it, and then you watch it decolorize as a test to see if there's an alkene present.
How do you spell the halohydrin? Is it
HALOHYDRIN, halohydrin. Questions? Yep.
Is the dot between the BH3 T-diff, is that a radical or?
So that nomenclature means, because the boron's electron deficient, it has a p orbital. So that molecule is the THF. So the THF supplies a lone pair of electrons, and they draw it as an arrow into that p orbital. It's there to help stabilize it. So basically, the borane comes as a solution. It's easier to work with in the lab. So it's the word here is dative. So it's a dative bond that coordinates from oxygen to boron to stabilize it. So one thing on your slides, under oxidation state 3, that should say sp2, not sp. So now this is where we're really going to focus on counting the oxidation state, whether it's going up or down, so we can classify reactions as oxidations or reductions. And then within that, we can develop this intuition about what we're starting with and what we should end up with based on the reagents that we're using. So we defined oxidation state as the number of bonds from a carbon to a heteroatom. And then these are the common heteroatoms that we've seen so far in organic 1 and 2. And the chart you see here, this table, it's just increasing the oxidation state. So we start with methane, CH4, that's oxidation state 0. And it's going all the way up to carbon dioxide at oxidation state 4. And then in between, we're just increasing. So we go from methane to methanol. The hybridization of the carbon, you can see in the row as that changes. So when you go up from 0 to 1, the carbon's still sp3 hybridized. But now when you go from 1 to 2, you're making a carbonyl. So you have 2 bonds at oxidation state 2. It's sp2 hybridized. 2 to 3, it remains sp2. And then the highest oxidation state for carbon is 4. And so now it's sp hybridized. So an increase is called an oxidation. And notice these jumps here. So 0 to 1, you can go 1 to 2, 2 to 3, and then this one right here, 1 to 3. So that the difference between them can be 1 or it can be 2. And that, again, will all depend on what reagents you're using in the reaction. So a decrease is reduction. So 3 going to 2. 3 going to 1, 1 going to 0, anything like that where it's decreasing in number. Any questions on just figuring out oxidation state? So we're going to start by looking at the preparation of alcohols. So alcohols at oxidation state 1 from carbonyl groups. So they can be at oxidation state 2 or 3. So in essence, we're looking at right now reductions. So the carbonyl group is polarized that way. Oxygen has its 2 lone pairs, so it's going to get delta minus. The carbon is therefore delta plus. So what is the plus telling you? The carbon is electrophilic. So in our general mechanism, that means the reagents we're using have to be nucleophilic. So that carbon's going to accept electrons from whatever reagent we're using. And when it does that, because we said we have to obey the Lewis dot, if we're forming a new bond to that carbon, an existing bond has to break. So of the double bond, the weakest part is the pi bond, so that's going to break. So if we have a nucleophile supplying electrons, those electrons are attracted to the delta positive carbon. So that's going to form a nucleophile carbon bond. And then we break the pi bond and push electrons onto oxygen because it's delta minus already. So a couple things happen here. The oxidation state changes and the hybridization will change. So again, just be comfortable with all of those concepts because we're putting them all together now to understand again how these reagents are affecting the carbon. So the preparation of alcohols from carbonyl containing functional groups is formally a reduction. So oxidation state 3, we can take a carboxylic acid or ester. We can reduce it down to oxidation state 2, and then that will be further reduced to oxidation state 1, which is the alcohol. Or we can take aldehydes and ketones, reduce them to alcohols. And then within that, based on what functional group you're starting with, you'll end up with a very specific class of alcohol. So you can memorize that, or it's kind of intuitive based on the carbonyl group you're starting with. Yep.
So what you showed was a 2 to 1. What would a 3 to 2 to 1 look
So if it was at oxidation state 3, so I'm going to just show an ester.
So it's like multiple steps there.
Right. So the issue is, again, when you're starting with 3, it doesn't go like 3 to 1 directly. It proceeds through 2. And because it's still 2 in a medium where you have reducing agents, this can't survive. It's going to get reduced as well. So why don't we review functional group names and assign them to oxidation states. So we have 1, 2, and 3. So if we just focus on the first column, we can eliminate A and C. And then the second column, oxidation state 2, we can eliminate D, and that would get us choice B is the correct answer. So here they are structurally. So aldehydes and ketones are at oxidation state 2. Acids, esters, acid chlorides, anhydrides, amides, and nitrile are all at 3. And then the last row is showing you where in the IR you can expect to see those carbonyl functional groups. So we're going to look at these 2 scenarios here, the 2-stage and the 1-stage reductions. So the reagents to carry these out are called hydride reagents. So again, hydride is H minus. So we can't just have a bottle of H minus sitting around. It's part of a reagent. The 2 most common ones that are used are called sodium borohydride, so NaBH4, and lithium aluminum hydride. So why are these hydride reagents? So in the periodic table here, these boron and aluminum are in group 3, so they're trivalent. So when they're neutral, they look like that. They're electron deficient. So the reagent, sodium borohydride, it has 4 hydrogens. So when boron gets that extra hydrogen, it becomes minus, and it's balanced off by the sodium cation. So a way to think about that reagent is it's equivalent to supplying H minus. And then the same thing for lithium aluminum hydride. Those are reagents that add H. Reagents that add carbon are called carbanions. That's what we'll focus on Wednesday. So I'm not going to talk too much today about these, but they're called organometallic. You have something organic, it's negatively charged, and then it has a metal cation, so organometallic. Those things will add carbon nucleophiles to carbonyls. But today we're just looking at H-. So let's just show something. We'll take propanal, so a 3-carbonaldehyde. Sodium borohydride is a little bit weird in the sense that you have to use a polar protic solvent, like an alcohol solvent. It's weird because the sodium borohydride is supplying H-. So you would think the H- is just going to react with the alcohol. It does to an extent, but it's also going to reduce that carbonyl. So sodium borohydride methanol, when we reduce that aldehyde, what class of alcohol is it going to produce? So it has to be primary. So that's the alkoxide intermediate. It's going to get protonated. And we end up with a primary alcohol. So this would be 1 propanol. And then maybe I'll write these numbers in blue. So the oxidation state was 2, and it gets reduced to 1. So an aldehyde, when it's reduced, will always form a primary alcohol. It doesn't matter what else is bonded to the rest of the carbon chain. So say you were starting with the ketone propanone. What class of alcohol does that have to be reduced to? Secondary. So ketone is always reduced to a secondary alcohol. So 2 is going to 1, that's a reduction. And then based on the location of the carbonyl, you can predict what class of alcohol it's going to form. And again, keep in mind what we talked about at the beginning. How do you know the alcohol is there? You run the IR, you see that nice big stretch from 35 to 3,000. Questions? One thing that's important in these mechanisms is how the hydride reagent is approaching the electrophile. So I have this carbonyl group here. The carbon is sp2 hybridized. We have R1 and R2. So depending on what those things are, this oxidation state can be 2 or 3. If this is H or carbon, you have aldehyde or ketone. If it's a heteroatom, then it's at oxidation state 3. It can be an acid, ester, amide, whatever. The nucleophile will approach that electrophilic carbon at an angle of 109, as measured from oxygen, carbon to the nucleophile. Can you think of a reason why that is? See, that's sp2 hybridized. This is sp3 hybridized. You remember what the normal bond angle for sp3 hybridized carbon is? It's 109. So the nucleophile is approaching at a trajectory that will mimic the hybridization that carbon is becoming. It's not going to approach from some weird angle which would cause the carbon to have to do some movement in terms of that bond to achieve that hybridization. So it's sort of like aircraft approaching an airport. You know, they have to get in these specific sort of highways in the air before they, lower their elevation and land. So that trajectory is important in describing how the nucleophile will attack. And I find it interesting, you may not, but people have proved this through X-ray crystallography by putting functional groups close to one another. And then they'll orient certain ways, and then the X-ray sort of takes a picture of that. How is a lone pair facing an electrophilic carbon? Someone's revving up the old crotch rocket out there. So how does it change based on oxidation state? So this is a key part of that question about 3 to 2 to 1. So with 2 to 1, it's just an addition and then protonation. So this would be for an aldehyde or ketone, you just get one addition because the reductions already happen from 2 to 1. And then you do your workup where you adjust the pH and the oxygen gets protonated as shown here. When you start at oxidation state 3, when you start at that, you get an addition. So the oxidation state is being reduced to 2, But now what's important is what that group is there. Because instead of being protonated at this stage, the negative charge on oxygen is going to collapse back to form a pi bond. That's going to eliminate off that leaving group. And now you're back to oxidation state 2. And so essentially what will happen is that will undergo a second reaction. So the nucleophile sees that. It's going to attack that carbonyl. You get your lone pairs. And now you've reduced it to oxidation state 1, which can be protonated. So it matters what reagent you're using and what oxidation state you're starting with. Questions? So what can we use it for? The two reagents, sodium borohydride and lithium aluminum hydride, have different reactivities. So you see the oxidation state listed here, and then you see the stoplight system. So sodium borohydride is only green lit for oxidation state 2. So it only acts on aldehydes or ketones. If it sees an oxidation state 3 functional group, it's not strong enough to react with it. But lithium aluminum hydride is strong enough to take down anything. So oxidation states 2, 3, or 4 it will react with. The bottom table further shows you what you're starting with in terms of the oxidation state, then the reagents down this column, and then the class of alcohol you'll end up with. So really what do you need to remember is ketone. So a ketone, no matter what you use, is going to a secondary alcohol. Everything else is going to primary. A question you might have is, what about how do we make a tertiary alcohol? In that case, we have to use the carbon anions, which we'll learn on Wednesday. I think we have two quick. So the substrate's the same, but the reagent is changing. So you have this polyfunctional molecule. We're treating with sodium borohydride. We have an aldehyde at oxidation state 2, an ester at oxidation state 3. So sodium borohydride only goes after oxidation state 2. And because we're starting with an aldehyde, that must form a primary alcohol. So when you look at the possible choices, which one is the best fit? So B. The ester has to stay the same. The aldehyde is reduced down to oxidation state 1, and it ends up being a primary alcohol. So that's falls into that reagent is called chemoselective. Even though it's a reducing agent, it only acts upon certain functional groups. Yeah.
So if you use the other one with aluminum, would C be the product? Because it would go after both of them?
Two problems we wrote for both of these. Yeah, so that's the next question here is you're using the lithium aluminum hydride. So this is both 2 and 3. So the oxidation states are 2 and 3. They both have to go down to 1. So C would be the best answer because it's reducing them both down. Again, the aldehyde is a 1-stage reduction. The acid to the primary alcohol is a 2-stage reduction. So lithium aluminum hydride, it's going to see all the oxidation states and just hammer them to 1. So on Wednesday, we'll look at adding carbon anions, and that'll allow us to access tertiary alcohols. Get through